Stat students, welcome back to section 8.3. We're still hypothesis testing in this whole chapter, and hopefully after 8.2 you've got a good feeling for the 5 steps, what they look like, where we find things. So now, just like we did in confidence intervals, remember we started off with using our z values in our confidence intervals, and we're looking for mu and all those things. So section 8.3, we're going to be kind of run parallel to that. What if we don't have our population standard deviation? That told us that we needed to use our t for our critical value. We do the same thing when hypothesis testing. So let's do a quick run through over on the right hand side here of all our symbols. You know these at this point, and you're tired of me repeating them. Everybody knows x bar, right, is our sample mean. Mu is our population mean. So remember, samples versus populations. And then in t values, we didn't know population standard deviation, sigma, but we do know S, our sample standard deviation. Everybody knows that N is our sample size, and a new addition to our symbols, degrees of freedom. Remember, that's the number of values that are free to vary after we do our calculations. It is N minus 1. Keep that in mind. Also, because it's called t-test for a mean, hypothesis test, we're going to be using our t's for our critical values. We are also going to be calculating a t-value. So, t-test for a mean. Sigma is unknown, so we are going to use S. This seems like a really great place for me to give you a list of data and have you use a TI-84 or some other calculator that will calculate your stats for you, and you find S, you don't know the population standard deviation. Typically, our N is less than 30. Look first for standard deviation, sample or population. Look second at the sample size if in doubt. This is important. I wrote it so small. I wish I had made it larger. Here is our calculation. When we go to find our test statistic, we are going to calculate t. This formula we've used before. T is equal to x bar minus mu. We're going to be given a sample mean. We're going to know the population mean. So x bar minus mean all over the sample standard deviation divided by the square root of n. If you can see the pattern of the formula for our test statistic, it is the same as in section 8.2 when we found z. We just knew x instead of x bar. We knew sigma instead of s. We are going to go to table F in Appendix A. That is our T table. My students, you've probably got a golden colored sheet with your T table on it, right? So you have that. It's also in the back of the book. I can't remember what page, 790 or something like that. And somebody pointed out to me recently, we have so many rounding rules. If your degree of freedom is greater than 30 and it's not on the T table, say it's 44 for your degrees of freedom, you round down, so you'd go to 40 for your degrees of freedom, not to 45. So one more rounding rule. We typically don't have, very seldom do we have a sample size greater than 30, but if we do, because we don't know sigma, round down on that table, you're technically going up the table because you're going to the smaller degree of freedom. All right, so I am sure that you remember our procedures for hypothesis testing. Well, it's really similar for T as it is for Z. This is the traditional method. Remember in section 8.2, we also talked about the p-value. We're going to do that as well. I'll try to talk fast. So step 1, everybody knows to find H sub O, H sub 1, and identify our claim. And then you're going to find your critical value using table F. This is our T critical value. After that, you're going to calculate your test statistics. That's that formula I just highlighted. T is equal to x bar minus mu all over S divided by the square root of n. After that, you make a decision. Are you going to reject or not reject H sub O? And everybody's favorite part, summarize the results. There is not enough evidence to blah, blah, blah. So the same steps. The only difference is step 2 and 3. In step 2, we go to the t table instead of the z table. In step 3, we use a slightly varied formula to calculate t instead of z. So let's find a couple of our critical values before we go any further. I used to have a t table. Oh, I didn't. Okay. So let's see. Find the critical value for alpha equals 0.05 and n equals 17. So first thing, right, we're going to make sure we mention the degree of freedom. Degree of freedom is equal to 16. Make sure you use that. It's right-tailed. We still have ourselves the symmetric curve, only remember we have a smaller sample, so we've got, our data isn't quite as accurate. So it's right-tailed, which means my mu is here in the middle. It's going to be up here. So that means it's going to be a positive critical value. When you look that up, I believe you're going to get a critical value of 1.746. Remember, our critical values for t's are always 3 numbers after the decimal. Z's are 2. So it does kind of shout at you if you know what you're looking for. Check the table, make sure you get the same thing. Number 2, find the critical value for alpha equals 0.01 and n equals 23 for a left-tailed test. I forgot to mention on number 1, probably should do that first, right? On our t-table, we do have a one-tailed alpha or a two-tailed alpha. You don't have to do any dividing by 2 for our alphas. We just look at the one-tailed. So if our alpha for number 1 is 0.05, you go to the one-tailed 0.05 and then to your degree of freedom of 16, which got us that 1.746. So left-tailed, alpha is 0.01, so it's going to be shaded down here. And our degree of freedom, right, is 22. Don't forget that. So it's a one-tailed test, so I'm going to go to 0.01 for a one-tailed test. And I'm going to go to my degree of freedom of 22, which is going to be like a 2.508. Now use what you know about, remember on a standard normal distribution, mu equals 0, so that has to be a negative. So if it's left-tailed, we're going to use a negative value. If it's right-tailed, we use a positive value. So watch that. That makes a big difference when you do your test or find your test statistic. So what about number 3 then? Find the critical value for alpha equals 0.01 and n equals 19. So that means, right, this and this, the two shaded parts are 0.10. Degree of freedom equals 18. So I'm going to go over to my alpha is 0.10 in the two-tailed part, the bottom column or bottom row, and then I'm going to go down to my degree of freedom of 18. I believe that gets you a critical value of 734? Double check my math. Now keep in mind, use what you know. It's this value and this value right here, right? So it has to be positive and negative. So if it's left-tailed, it's negative. If it's right-tailed, it's positive. And if it's two-tailed, it's a plus and a minus. So keep that in mind. The table doesn't give you the signs. You have to know what you're looking at. All right, so that's finding critical values. Hopefully you're good. We've done a lot of these, so I didn't feel like I needed to go forever. So now let's talk about the p-value method. So not traditional, but looking at the p-value. Remember, the p is actually the probability or the area under the curve. We're comparing how much is shaded. But there's a lot of similarities here. Step 1 is always H sub O, H sub 1, and the claim. Identifying the claim is important for step 5. In step 2, you're going to compute your test statistic, which is still finding your t. It's the same formula. T is equal to x bar minus mu all over s divided by the square root of n. Nothing has changed there. Same formula. It's still our test statistic. Step 3 then is to find the p-value. This is the interesting part. This is where we go into the t-table, and it's very imprecise. So let's see how I can say that. For step 3, jump into the t-table, and it is very imprecise. With t's, it's not my favorite method to do the p because I like things to come out very clear. We know exactly what the p-value is. It's very imprecise, but we'll look and see so you can see what's going on. Step 4 is always make your decision. Are you going to reject or not reject H sub O? And step 5, summarize those results. So before we do an actual hypothesis test, let's make sure that you know how to find the p-value by jumping into the t-table. So I got a big t-table here so that I can help myself out. So this is step 3. So number 4, it says my t-value, my test statistic is 2.321. My n equals 15, and it's right-tailed. So one-tailed, right? My degree of freedom equals 14. Still have to use that. So what I'm going to do is I'm going to jump into the table at t equals 14, or sorry, at degree of freedom equals 14. So here's my degree of freedom of 14, and I have to go across, and I have to scooch this a little farther. If my t-value is 2.321, I'm looking for where that would fall. Well, my t-value, 2.321, would fall between these two values. It's one-tailed, so it would fall between those two values, a 0.025 and a 0.01. So P is somewhere in between those values. That's what I was talking about, very imprecise. 0.25 and 0.1 are my two values. 0.1 is actually smaller. If you read it from left to right, it goes from smaller, it goes from larger to smaller. So 0.01 would be my smallest possible p-value, and 0.025 would be my largest possible p-value. Then we'll use that to compare to alpha like we did in the last section. So number 5, see if I can just leave this here, make sure I'm good. My t-value, notice, is a negative 1.415. My degree of freedom is 23. Now, I just know that the negative on that 1.415 means that it is a left-tailed test, right? So I'm just going to ignore that. I'm going to highlight my degree of freedom of 23. And I'm going to look for 1.415. Where would that fall? 1.415 would fall in between these two values. It is a, I can't see underneath there, is it a one or two-tailed test? Let me just scooch this over. It's a two-tailed test. So when I go up for the two-tailed test, it's going to be somewhere in between those two values. So a 0.20 and a 0.10. So I know that my p-value is somewhere in between 0.10 and 0.20. That's the best that I can do. I know that's my p-value. Again, I wrote those in the opposite order from up here because the larger values are to the left and they get smaller. So last but not least, number 6, it says that it is a left-tailed test, so one-tailed. My degree of freedom is 16. I just know that that negative tells me that it's left, right? So for number 5, I probably should have put positive and negative. Sorry about that. But we know that we just ignore that sign. Let me go ahead and highlight my degree of freedom of 16. And 1.862, ignoring the sign, would fall right here, 1.862. You can barely see that. So it would fall in between those two values. For a one-tailed test, doesn't matter if it's left or right, I go to the top row. So my p-value is going to be somewhere between a 0.025 and a 0.05. So that's the very imprecise. That's why I don't love p-values when I'm working with no population standard deviation. But we're going to do the same thing. We're going to compare them at the end. So that's where our p-values come from when we go to step 3. So now let's do a traditional method. Let's do a quick test. It won't take us long because you've gotten the procedure. A study claims that the average number of broken legs per week at a hospital is 16.3. A random sample of 10 weeks has a mean number of 17.7 broken legs, sample standard deviation of 1.8. Is there enough evidence to reject the claim at alpha equals 0.05 level? So let's do a quick run through. Before we even do our hypotheses, let's see what we've got here. Average number of broken legs per week is 16.3. That's our mu because the next sentence says in a random sample of 10 weeks, so here's my n, right, has a mean number of 17.7 broken legs. So there's my x bar. Look at all this information they're giving us. With a sample standard deviation of 1.8. And then we, of course, know that alpha is 0.05. So everything we need to know, hopefully by identifying the mu right at the beginning, we know what our h sub o and h sub 1 are. So h sub o, remember, write out the whole thing. H sub o, we're saying that mu equals 16.3 because our null hypothesis is always inequality. The average number of broken legs per week is 16.3. Is there enough evidence to reject the claim? Does it tell us that we're looking for more or less? It doesn't, right? So it's just going to be a mu is not equal to 16.3. And their claim is that there are 16.3. So our claim is our h sub o. Compute the test statistic. So we've got ourselves a math problem to do. So t equals x bar minus mu, right? We said x bar was 17.7 minus my 16.3 mu all over my standard deviation divided by the square root of n. So I've got myself a quick calculation. Double check, make sure that you get the same thing when we compute our test statistic. I got a 2.46. All right, so now I am going to find, oh, I should have found my critical value first, shouldn't I? This was actually step 3. Wondering what was happening. So my critical value, I've got to go to my t table. My degree of freedom is 9. This is two-tailed, right? It says that my mu is 16.3, and I'm wondering if it is something different. So it's two-tailed, degree of freedom 9, and my alpha is 0.05. So it looks like my critical value is going to be a 2.262. And since it is this dividing line right here for my critical value, it's got to be a positive 2.262 and a negative. All right. So now we just have to make a decision. So if 2.262 is my dividing line and my very sloppily shaded little part is my rejection region, my test statistic was at 2.46. So on the positive side, my test statistic comes out to something like right here, right? This would be 2.46. So my test statistic is inside my rejection region. So I am going to reject h sub o. And last but not least, summarizing the results, my claim was H sub O and I rejected H sub O, so I'm going to go to my table and I am going to say something like there is enough evidence to claim, wait, what am I going to, I couldn't read my own writing. There is enough evidence to reject the claim that the average broken legs, average number of broken legs is 16 point, was it 3? 16.3. Everybody asks if we have to do this part. Yes, because that's important, right? You're summing up everything that you just found. You are telling me there's enough evidence to reject that claim based on your statistical calculations. So there is a hypothesis test using our critical value as a t. We had to use t because we didn't know sigma, and our sample size was also quite small. So that's why we had to do that. But the number one reason is sigma. Let me just mention this one, chocolate chip cookies. The average 1 ounce chocolate chip cookie contains 110 calories. I've got a random sample of 15 different brands, and the list is the number of calories in each cookie. At the alpha equals 0.01 level, is there sufficient evidence that the average calorie content is greater than 110 calories? Use the traditional method. So here's the thing, we would need to go to a TI-84. We would need to find out what X bar is. We would also need to find out the sample standard deviation with this N of 15. We would not use sigma, remember. We don't have the population of all the cookies. So you have to use your S, sample standard deviation. Okay, I know that I'm droning on and on, but I feel like we need to do a p-value test so that you can see what's going on. So a researcher claims that the mean wait time at a doctor's office is at least 18 minutes. Well, right here is my mu, right? A random sample of 15 people has an average wait time of 20 minutes with a standard deviation of 4.2 minutes. At alpha equals 0.05, test the researcher's claim using the p-value. All right, so null and alternative hypotheses. Whoops. So null hypothesis is always our equality. So mu is equal to 18. I labeled stuff as I went. I hope I didn't rush you. It does say that the researcher is claiming that the mean wait time is at least 18 minutes. So that's got to be greater than 18 minutes, and that's our claim, right? So you have to read to find that claim. So let's compute our test value. Test value or test statistic is always your t equals. We're doing this in this order because we're doing the p-value test. So by the way, if I were to draw this, here's my mean at 18. I think that it's higher. So let's do a little math. So let's see, it's going to be x bar minus mu, so 20 minus 18 all over our standard deviation divided by the square root of our sample size. Take a pause, do a quick check. I got a t of 1.8443. Make sure you get the same thing. I went out 3 decimal places because p-values are, so now this is the weird p-value. When I go to my table, p-values are imprecise. This is going to be an inequality. The p-value is somewhere in between these. So I'm looking for this 8.433. So I do 1.8443 with my degree of freedom as 14, right? Because my sample size was 15. So I'm going to go into my table. At degree of freedom 14, it's a one-tailed test. So let's see, 14, 1.843 is going to be, 443 is going to be somewhere in between 1.761 and 2.145. I go up for a one-tailed test, and it looks like it's between a 0.05 and a 0.025. So let me move this over. 0.025 and 0.05. So that's what's shaded. I already know from my problem that alpha is equal to 0.05. So this shaded area right here is 0.05. If I were to shade in my p-value somewhere between 0.025 and 0.05, that p-value would be shaded like somewhere in this range, right? Or up to the line. So this is my p-value. That p-value is lying inside the whole area is less than or equal to my alpha. So that means it's in my critical region, which means the second time today, I need to reject H sub O. And then I would go on and I would finish that problem. Since I'm rejecting H sub O and my claim was H sub 1, I would say something like there is enough evidence to support the claim that the average wait time is greater than 18 minutes. You got the idea. Yes, you have to write it. We're going to skip it this one time. Don't tell. So don't forget for your p-values. If your p-value is less than or equal to alpha, reject H sub O. If it's greater than alpha, don't reject. Your p-value area would spill into the non-rejection region. That is it for 8.3. Sorry for the long haul, but we had a lot of stuff to talk about. Have a good one. I'll see you next time.